Thanks for the patience. This is the gotcha of having a talk after the lunch, particularly in Italy. So, thanks again for joining. I'm Alberto Massidda, and today we're going to talk about how we can teach machines to take decisions, to take informed decisions about whether to carry out an action or not. So a brief couple of words about who we are. We are Sourcesense. We have been existing since almost 20 years. We are a big system integrator and consulting company devoted totally to open source technologies. We have branches in Milan, Rome, Cosenza, and London. We have our expertise in DevOps, so Kubernetes, the cloud, the monitoring, everything revolves around containers. Also integration, mobile, backend and front end, and of course data science, so machine learning, big data, and stuff. This presentation, of course, is open source. So, today I'm very excited to be here because for the first time I'm going to carry out a big load of math into a Codemotion talk. So brace yourself. I will try to be as clear as possible. I will try to explain the most I can. This is because it will be very easy for me to do a very high-level talk like reinforcement learning in 5 minutes, but it will not provide any value for anybody here. So I'll try to be thorough as possible. So we'll define briefly the reinforcement learning. Then we will expose the concept of a Markov decision process. Then we're going to talk about the two main approaches in the reinforcement learning, which is the deep Q learning and the policy gradients. And then how we can have the best of both worlds with the actor-critic model. And then we're going to have two case studies with AlphaGo and the technology that sits underneath, which is the Monte Carlo tree sampling. And also we're going to talk about AutoML and how can some neural networks be aggregated by architecture search. So in reinforcement learning, we deal with an agent into an environment. The agent performs actions and the environment responds with a feedback to the agent that we call reward. And also with a new state that the agent is moved into. And so the agent can take another action, which will carry out another feedback, another new state, and so on. And we model all of this as a Markov decision process. A Markov decision process, or MDP, is a mathematical framework for modeling decision-making in situations where the outcomes of your actions are partly random and partly under the control of a decision maker. So your environment contains a certain level of stochasticity as opposed to a deterministic environment in which the same action always yields to the same outcomes. For example, think about you're in a video game. You open a door, there's nothing. You go around, you go to the same door, open it, and there's a monster behind that. So the same action didn't yield the very same state, because that was not deterministic, but it was a stochastic environment. Any Markovian decision process can be defined by the following tuple. So in S, defines the set of all the possible states my agent is allowed to be into. A is the set of possible actions that are legal in this process. R is a probability distribution of rewards given a state and action pair. So it's a function that given a state and an action you perform in that state samples probabilistically a reward as a full distribution of probability of events. So it assigns a very small probability to each state action pair. Then we got P, which is a transition probability. And so it's the probability that from a state you can go into another state belonging to the set S. And is modeled again as a distribution over the next state given the state action couple. And last but not least, there's a gamma. which is a discount factor. A discount factor is like a penalty that is applied to the rewards that you get if you go too much further in the time ahead when you're estimating the reward that you want. So whenever you do an action and take their immediate reward, that will not be penalized. But if you try to do 3 actions in a row to get the 3 rewards and try to estimate the fitness of your state, you get discounted. This is done to actually encourage your agent taking action, not looking too far in time, but only in the immediate, okay? So how does it work? Time 0 at the beginning, the environment samples an initial state as 0 among the probability distribution of all the possible states. Then, in an infinite loop until the end of a game, for example, an agent selects an action, A, at a certain time t. How? We'll see in a few moments. The environment then samples a reward from R, given S and A. The environment also samples the next state as t plus 1, because it's a state which is plus 1, given the fact that we are at the time t, from the transition probability distribution. An agent receives the reward and the next state as t plus 1, and then decides a new action. A policy, P star, is the thing that the agent uses, which is a function that maps from a state to an action, and is the thing that specifies what action is to take at a given state. And the goal of all this valzer is to find a function P star that maximizes for the agent the total reward that it can gather by taking actions in different states as the game rolls. And this is expressed as a sum for all the rewards that you get discounted over time. So you can see that gamma is as a power, which is the power of time. So the more you go further in time, the more the gamma discounts the rewards, actually making really difficult to see for a lot of steps ahead in time what is the reward that will be. So this is a very simple MDP automata in which you can see the states, which are the nodes, then the transition you can have, which are expressed as the links between the nodes, and you have the goal state, which is the omega node. Here you can see a random policy. So the agent takes a random decision to move into any state near. So an agent could be dropped anywhere and could be started moving randomly because every state, every action is equiparable. Instead, this is an optimal policy. This is an example of no matter where your agent is dropped into the graph, the policy will always suggest the best action to go to get in the minimum number of hops to the omega. So for example, okay, great. If you're here, you can go straight ahead and in 3 hops you get to omega. Or you can go 1, 2, 3, or you can do 1, 2, 3. You always get in the minimum number of jumps. So how can we find the optimal policy P star? Well, usually we just have to find everything that maximizes the sum of that, of the rewards. But the problem is that we are in a probabilistic, in a stochastic environment. So because the initial state is sampled, you can be dropped anywhere, depending on a probability, which may be higher in some nodes and less. It must not be equal probable. I'm not assuming that. And we deal also with transition probabilities. So whenever you take an action, you may not get exactly into the same state you're expecting. So we use a notion that comes from statistics, which is the notion of expectation. The expectation is expressed mathematically as the sum of all the outcomes that a random variable can have, like for example rolling a dice, times the probability of having that outcome. So if you have a fair dice, a roll dice, the expectation over the dice is the probability of having 1 times 1 plus the probability of having 2 times 2, the probability of having 3, and so on and so on. And you will see that you will have 3.5 as the expectation over a fair dice. If you have an unfair dice that strikes 6 with a probability of 80%, you take the expectation and you will have a value, which is the sum of all these outcomes times the probability of having that outcome, that is very close to 6. It was going to be 5 and something, but it's this to express you that the value you should expect from that random variable is actually very close to that one. And the optimal policy in this case is the policy which maximizes the expectation over the total cumulative reward that you get by following the policy. So how can we measure the reward we can get from a state? Well, you see, following a policy produces trajectories, which means you get into a state, you take an action, you get a reward, and you get a new state where you get a new action, you get a new reward, and so on. And you could actually count the rewards in the trajectories that your policy actually generates for you. To measure how good is an action in a state, we exploit this by introducing 2 special functions. The first is the Q-value function, serious math here, coming ahead, and it's the expected cumulative reward of the trajectory that springs from taking an action A in a state S and then following the policy. So you can see it's a summation over all the cumulative reward. If you take action A while being state S, and follow the policy. And you expect over this, because of course, not all the actions are certain, because I probabilistically sample my action, given the most probable one, and probabilistic, I sample the next state, and I may get a different reward. So I use the expectation to average out all this uncertainty. The second function, the value function, tells me the value at a particular, so this function emits a score for how good was an action in some state. This one instead emits a score for the total value of the current state I'm in. So it's the expected cumulative reward of all the trajectories that may stem from that node. Or in other words, it can be the expectation over all the possible Q values for all the actions I can take in some state. That formula seems complicated. It's just telling you for all the rewards I may get for performing any action, the expectation over all the actions that this policy can suggest me. A very nice property of the Q function is that it is recursive. So these are the optimal Q functions in which you take the policy that maximizes the expectation, max E. But this function can be rewritten as follows. So you have the expectation over the immediate reward that you get when you take a decision, plus the estimate, the Q value, for the state you have landed onto. And this makes sense because whenever you want to explore something like this, the optimal decision is a function of the value of one of these links. You want to take the link which is the highest because it's the one that gives you the best reward. But at the same time, you want to land over a node that is most promising. So use the Q value function as a compass in an orienteering game where you want to go to the highest link that brings you closer to the best node possible. The consequence, and this is the mostly dreadful Bellman equation, and which is you may have read if you have tried to read our reinforcement learning tutorial, always boils down to this Bellman equation. And the takeaway from all this is that since it's recursive, the best policy corresponds of taking the best action, which is pointed out by the Q star, in any single state, on any single step. So in order to get the maximum score, you just have to do the best action for each step you go around. You don't have to worry about the future of all the possible states. Just try to do your best in every state, and you will end up with an optimal result. So we only need to find the Q star, something that given a state and given action, gives a score, and then you pick the highest score, and that's your policy. You find this, and you're done. We have solved the task. So how can we find the Q star? Well, in deep Q learning, we use a function approximator to estimate the optimal Q star, like, for example, a neural network. So a neural network is another function Q, a Q value function, that takes state and action, and also some weights, theta, which are the weights of your neural network, and tries to approximate as much as possible the real Q star, which is the real best function possible. And by the way, here's your loss function to train into your favorite deep learning framework. So the loss function is an expectation over the value that your network is sampling, QSA theta, minus y, which is the ground truth. So you try iteratively to make that thing as close as possible to the ground truth y. And y is just the expectation over taking the best action over and over again. So you have to learn what is the best action, and you have to learn how to approximate this. The nice thing about this stuff is that you don't know the ground truth. You just let your agent randomly play until it understands over time what are the best actions out of experience. So that thing, y, is modeled as time rolls by, and you then find out what was the best action, since you try to explore your state space as much as possible. And your agent, at the same time, learns what is the best action to carry out when you get into a state that you've already seen. And this is all you need to start training an agent. So the hello world of reinforcement learning is playing Atari games, because are complex enough and are simple, yet simple enough to be modeled. So this is breakout, or arcanoid, as some of us know. The objective is to score the highest score possible. You are this paddle hitting this ball, the red pixel, breaking out the bricks. You have to clear out all the bricks. The state, in this case, is the raw pixels of the game. So I feed the pixel of the game, which is just a matrix of numbers, to my neural network. The actions are the game control, so left, right, A to fire the ball, and nothing. There's always one plus action, which is stay still, don't do anything. And the reward is the score increase, decrease at each time step. You break a brick, you +1. You lose a life, -1. This is the neural network, actually, that plays Atari. So we start out, it's a very simple convnet, if you see. It's just a 4-layer deep convolution network. You use as a state 4 frames, the last 4 frames of your game. And you do RGB to grayscale conversion, you downsample them, you crop useless information, and then you stack them, you concatenate them all around. And then you pass this into this convnet, which is 2 convolution layers, then a fully connected layer, so you flatten everything out. And then you have the 4 outputs of the last layer, which corresponds to the 4 possible actions. If your game is much more complex, you output more outputs. And you might appreciate how a single feed-forward network computes the Q value for all the actions from the current state. So it's really efficient to use this one. This works, so you let the game unroll, the agent loses a lot. After 20 minutes of training, he's able to play, and after 2 hours of training, he's able to play like a pro. It's also able to dig a tunnel into the bricks and having the ball break all the bricks from the upside. There's a problem with this. The problem is that learning from batches of consecutive samples is problematic. So the naive assumption is that we let the agent play, get rewards, train on the rewards, and then keep playing. The problem here is that a state and the next one are correlated, because you have some parameters that yield some action, and then you have a new state, and this state is tied to the action and to the parameters themselves. So if you have the parameters which are correlated to a next state, and the state is correlated to how the parameters change because you in turn keep upgrading your parameters, it can lead to bad feedback loops. For example, you are driving a car, you have a U-turn, so a very long left turn. Your agent has the target of staying into the road, not going off-road. Starts steering off the left, plus reward. Keep steering, plus reward. Keeps steering some more, the turn is almost finished, and it has learned that steering on the left always yields to positive rewards. You know what happens when the turn ends? Your agent keeps steering because it expects to have a positive reward. This is a bad feedback loop because you pumped too much the probability that turning left is a good idea. We can fix this by using a thing called a replay memory. So the replay memory is just a big table where you store a state, action, reward, the next state tuple. And so you sample these tuples as you play the game, but you don't train your network over the last state, but over random mini batches that you sample from the replay memory only. And then you keep playing with the updated parameters. So you might turn left, but actually your network is training of another episode in which it was turning right or going straight ahead and so on. So you're actually decoupling the training phase from the learning phase instead of doing that sequentially. And this breaks the bad feedback loop. You may also want to introduce a small chance of taking a random action instead of choosing the best informed decision. And this is mainly to explore the possible state space without greedily going after something that has proven to be effective, because you want to really explore the state space. Otherwise, you will overfit the first actions. And you may want to use the simulated annealing technique by which you define a high temperature parameter. And the temperature yields to random actions, but as the temperature drops down as the game rolls, the amount of randomness will fade out and only informed decisions will be made. So you can pre-populate your replay memory in the beginning of the game with random actions, thus exploring a lot your state space, and then start only taking decisions based on your policy that you've learned by doing replay memory. Another problem is that the same network is predicting Q to choose the action and is acting as Q star to predicting Y at the same time. Remember here, I told you that this max Q with the A prime, S prime is the very same network which is trying to predict the best action. This is because you explore the space, you gather the best action in time, and so you're able to output a very good Y. And at the same time, you try to make this as close as possible to the best action that every time you were shown after you take the action. And the problem here is that as you hopefully train and get better, you keep using the current weights to move the Y a little further every time. So you decide the Y is at a certain point, and you head for that with your state, with your agent. The Y changes because the Y is generated by your network, and you keep chasing a thing which is a moving target. A way to fix this is by creating two networks, actually. So decoupling is always a good pattern. Two networks are called target and predict. Predict does a Q function estimation and updates its weight. Target is the one that calculates the V function, the value function, which is the base of the Y, and doesn't get trained at each step, but gets the weights of the predict, which is updated continuously, once in a while. This has the effect of stabilizing the Y you want to move against, because the target function stays fixed in a while. So each 100 iterations, you update also the value function, and you can move the Y. But it's like chasing somebody who takes breaks once in a while and lets you get very close. This stabilizes the learning, and so your learning is actually faster. All of this works very well when you have a very limited set of actions, actually, turns out. So with Atari games, with very simple decision processes. And this is because in Q-learning, we are improving our estimates of the values of the different actions. So you take an action, and you get punished or rewarded for taking that action. And so you have to build functions that emits an estimation for any state action pair. This is the definition of Q value function. But this only implicitly improves the policy, because if your policy is, for example, grabbing an object, you have to emit for every state action, so hand open, object here, now I'm bending this finger, okay, bending this other finger, okay, bending this one. So there's a lot of high dimensions into this system, because I have a lot of joints. Each joint can move almost independently. And so in order to grab an object, I have to model a very, very complicated Q function, because I am dealing with a high-dimensional problem. And this gets even worse if you have a stochastic space in which you try to predict an action from a state, and then your action turns out to be bad because your space is stochastic, and you end up in the wrong space, and you get the wrong reward. And so your function doesn't understand. Instead, it will be much easier to just learning a policy of closing your hand. So take 10 actions all together. Don't try to estimate every single action in a sequence, but bend all your fingers and keep moving until you have grabbed the object. By learning directly a policy from a collection of parameterized policies. And this is the notion of policy gradient learning. So in policy gradients, we are following gradients with respect to the policy itself, which means that we are constantly improving the policy, as opposed to the Q learning, where we just improve the actions and implicitly improve a policy. So for that, let's define a class of parameterized policies, and for each one, we define a value function, which is the total expected sum of cumulative reward by following a policy, and we want the policy that maximizes this. How do we do that? Well, now I'm going to blow your mind. We don't perform the gradient descent as we usually do in the deep learning, but we perform a gradient ascent. This is because if you think about it, clapping hands all over. Okay. This because in the gradient descent, we are trying to minimize a loss function, so which is the difference between the optimal and your decision. And we try to minimize this discrepancy. That's why we do gradient descent. You want to minimize a negative effect. Instead here, what we want to do is pump up the parameters that led to a good decision. So we perform a gradient ascent over those parameters because we want to maximize a function. So, and here is your gradient estimator. I don't want to actually go through the full deriving of this very complex equation because it's long as my arm. But what you want to actually see is that you have a summation over a reward trajectory, over the gradient of my policy, log policy actually. And this is your gradient update rule. So you have the theta parameters plus learning rate alpha plus time, the total reward of the trajectory that you've sampled in your policy, and the logarithmic of the network here that actually predicted that thing. The key takeaway here is these three things. First is that the gradient of an expectation is a hard thing because you are taking the derivative of probability, which is not an easy thing. So we go over that by sampling a large number of trajectories, and we average out the differences in the trajectories. And this is called Monte Carlo sampling. Monte Carlo sampling is a technique, comes from statistics again, by which you want to estimate a parametric probability distribution, which is very hard, and you don't know the distribution. So you take samples. You sample the outcomes, like rolling the dice. You don't know what is the function behind the dice. So you roll it, and you end up with a lot of numbers. And then you fit your hidden probability distribution over the outcomes of your sampling. This works only if the sample space is covered enough, so you don't have to sample always the same value. And also, please note that there is no transition probability. So whenever you go into a next state, is a function over the action that you took of the policy that specified, and over the probability distribution. But here you can see that the policy P actually is everything that you need to actually model the thing. And this is because the probability distribution is not affected by it's not a function of theta, of the network parameters. And this means that I don't have to model the transition probabilities to train an agent. I don't have to model my full environment. I just have to drop an agent in an environment, even though I don't know that, and the agent doesn't know anything about the environment. And the agent will learn. This is the mathematical way to say that this is a model-free algorithm. And that's what makes the reinforcement learning so successful in a lot of problems. And third, there is no value function. There's no Q or V here. And this is because we generate a trajectory, then we get into a reward, a certain, at the end of the episode when the game ends, and then we backpropagate that value across all the actions that there was in our trajectory. And this is very nice because I don't have to estimate anything. I just have to see how it ends and then distribute the reward among all the actions that make up my trajectory. So the interpretation of all this is that if the reward of the trajectory tau is high, push up all the actions of the trajectory. If the reward is low, push down all the actions, and time by time, sampling, and training, all the good actions will emerge as the yielding to always positive state action trajectories, and my agent will behave correctly. There's a problem here also. Policy gradients converge really slowly. This is because all the action in a winning trajectory gets pushed up, even the bad ones. But this is because I may make some mistakes. If I have to take a walk from Rome to Milan, I may make some mistakes in turning left or right, but in the end I will get there. If I reward all the actions, I push up also the mistakes. But this is okay, because by Monte Carlo, the effect of Monte Carlo sampling, this in the long run averages out. This is because the mistakes will not happen that often in winning trajectories. Why? So they will get pushed up, but they will get pushed down more and more often in bad trajectories. When a lot of mistakes will show up, all the mistakes will be pushed down. And so in the end, good actions will appear more often in good trajectories, which will be pushed up. And the mistakes will tend to appear in bad trajectories, pushed down. At the same time, lowering the chance of seeing a mistake in a winning trajectory in the long run. This works. But the problem is that we must generate a lot of samples through Monte Carlo to obtain this. And Monte Carlo must wait for the full episode of the game to get the final reward. So you have to wait for that. And as it wasn't enough, the random trajectories mean that you have a high variability between the rewards. And this means a high variability, high variance in the probabilities. And this leads to noisy gradient updates. And this slows down your training, so the learning will be really slow. A way to reduce the variance with a baseline is by having a smaller gradients update. How? Subtracting the cumulative reward that you get into every trajectory by a baseline. So you subtract a fixed baseline from all the actions. And this is because if you have a smaller reward, because the reward is part of the gradient update rule here, you will have a smaller gradient update. Smaller gradient update make for smaller training steps. And this leads to better and more stable training, actually. So a nice baseline is having the Q function as a baseline. So you subtract, instead of using your reward, use the Q value function at each time step to emit a reward, and you're not backpropagating the final one. And this makes for the most advanced algorithm to train the reinforcement learning agents, which is really the state of the art, which is the actor-critic algorithm. We are approaching the end. We define an actor, which is the policy, and a critic, which is the Q function. The actor decides which action to take, so it samples trajectories. And the critic tells the actor how good its action was and how it should adjust. And for each trajectory, you calculate the total reward, and you perform a gradient ascent of actor over Q value for each step in trajectory. And you do also the gradient ascent on the critic over the total at the end of the trajectory, minus the estimated reward Q value that the critic provided. Also, this has a nice side effect that since you perform update at each step and not only at the end of the trajectory, you have more frequent parameter updates. You speed up the learning. So now I want to introduce the first case study, which is AlphaGo. AlphaGo uses a neural network, of course, but uses a policy, which is no, it's not a policy, sorry, is an algorithm called Monte Carlo tree search. In tree search, since you're playing a game, your state space is like a tree. I take an action, you take an action. I take an action, you take an action. From any state, you can only have a certain degree of action you may have. So you select the best node, you perform a selection. And how you select that? You select the optimal node among the fringe of nodes that you can expand while you build the tree with an upper confidence bound, which is a function of the value of a node and the number of visits of that node. Then you expand the most promising node that has the highest upper confidence bound. And then you run a simulation. You play a game until you get to the terminal state. You get the reward, and then you backpropagate the reward from all nodes starting from this one up through the root, and you update the total value of each node. What you obtain here is that you try to tend towards the optimal nodes that have the best promising value, while exploring at the same time the nodes who have been visited less often. In AlphaGo, the evaluation of a leaf node, the selection phase, is a weighted sum of two components, which is a standard rollout. So it's a shell of softmax neural network that plays a game until the end, reports the value, and goes back. And then you have position evaluation, which is a 13-layer convolution value network. So it tells you the value of this node, which has been trained over 30 million of distinct position, state action, state action, state action, obtained through self-plays. And this is where AlphaGo plays against itself and improves. In AlphaZero, there's a slight modification. You don't perform any simulation at all, but what you actually have is directly evaluate the current node with a 19-layer CNN, so a convolution neural network with residual connections. And this is the difference between AlphaZero and AlphaGo. And this makes also AlphaZero faster to train because there's less computation going on. Instead, AutoML, you may have heard that Google Cloud puts at your disposal an algorithm that searches the best neural network for your data and derives automatically the best network. This is called AutoML, but it's a commercial branding term. In academia, it's called Neural Architecture Search, and it's invented by Google Brain. It's a gradient-based method for finding good architectures. It uses two networks, a recurrent neural network, which is the controller, that generates a string, which is a definition of a child network. The child network is trained over real data. You then sample the accuracy over the validation data, and use that accuracy as a feedback over the controller that learns how to generate better networks. Alan Turing will be really happy about these machines that create other machines. So you compute the policy gradients to update the controller on the accuracy as a signal generated by the children network. Here I left some references. You can find the slide I'm leaving to the organization, and you can really use this as a starting point. We are hiring data scientists, so please write to recruitment@sourcesense.com. Please leave feedback and rate this talk so we can come up with better ideas. Thank you very much for the patience. I'm over.